This is the review sheet for Calculus AB, the test on Rolle's theorem, mean value theorem, maximums, minimums, concavity, increasing, decreasing, first derivative test, second derivative test, and so on and so forth. So let's get started. First, find the critical numbers for f of x equals 3x to the fifth minus 5x cubed. Critical numbers are where the derivative equals 0 or does not exist. So we need to take the derivative, set it equal to 0. Look at what they have in common, which would be 15x squared, and factor as far as we can. So x squared minus 1 becomes x minus 1, x plus 1, giving us three critical numbers, 0, 1, and negative 1. If the function has a fraction, make sure you look also for where it doesn't exist, which would be anywhere where the denominator is equal to 0. Find the maximums and minimum values. I apologize if this is small, just make sure you're following along on your paper. Find the max and minimum values for f of x equals x squared minus 7x minus 8 on the interval negative 2 to 3. When we're asked to find max and min on an interval, you need to look at the critical numbers and the endpoints. So this is where you need to not do the chart, but take the critical numbers and the endpoints and plug them back in the original. So first, find the derivative, set it equal to 0. I get 2x equals 7, or x equals 7 halves. Double check, 7 halves is in fact in our interval, so that's good. So now I take the critical number, I may have more than one, but here I only have one. Take the critical number and the endpoints and plug them back in the original equation. So let's see. Oh, sorry, I wrote that backwards. We're going to be plugging in 7 halves, not 2 sevenths. If I plug in negative 2, that should give me 4 plus 14 minus 8. I think I'm getting 10. Let's see. Yes. And if we plug in 7 halves, that's going to be 49 fourths minus 49 halves minus 8. So that's negative 49 fourths minus 32 fourths. Oh boy, I'm getting negative 81 over 4. Let me double check that real quick. Yes, that's right. It's also negative 20.25 if you prefer the decimal. And then if you plug in 3, it's negative 20. So our smallest is the negative 81 over 4, so that is our minimum. Our biggest is negative 210, so that's our maximum. Remember, focus on the y values. The biggest y value is your max, the smallest is your minimum. Determine if Rolle's theorem applies to this function. Let's do that first. There's three requirements for Rolle's theorem. First, it must be continuous. Second, it must be differentiable. Third, the endpoints have to have the same y value. Okay, now, continuous, you mainly just need to watch out for denominators. That's your red flag. Differentiable, you need to watch out for absolute value and powers with fractions that have an odd bottom. So like x to the 1/3, x to the 1/5, x to the 2/3, x to the 2/5, and so on. Okay, that does not seem to be an issue here. None of those red flags appear, so we do need to plug in the endpoints and make sure they give us the same y value. That is a requirement. So we're going to get 1 plus 4 plus 4 plus 1, which is 10. And then if we plug in 3, we get 3 to the 4th is 81, minus 3 to the 3rd is 27 times 4. Oh goodness. Let's just do this. Save ourselves a little bit of time. X to the 4th minus 4x cubed plus 4x squared plus 1. Then we go to the table and plug in negative 1 and 3. And we get 10 for both. So we do get the same y values for both, which means Rolle's theorem does apply. Once you realize that, then your job is to take the derivative and set it equal to 0. So I take the derivative of my function, and I get 4x cubed minus 12x squared plus 12x, plus 8x, excuse me, and then set it equal to 0. I'll check it out and see what they all have in common, which is 4x, leaving us x squared minus 3x plus 2. You can factor that to be x minus 1, x minus 2. So we have 0, 1, and 2 as our answers. 0, 1, and 2 are our answers. Okay. Given the function 5 minus 4 over x, find all the c on the interval 1 to 4 such that f prime of c equals f of 4 minus f of 1. This doesn't actually say the words mean value theorem, but it is the mean value theorem. Anytime you see the derivative set equal to the slope formula, that's the mean value theorem. The mean value theorem just has two requirements, that you be continuous and differentiable. And we do have a red flag show up here. We have a denominator, and we can't be equal to 0. However, 0 is not in our interval, so we're okay. As long as our interval works, the function is going to work. So since 1 to 4 is all good, we're all good to go forward with the mean value theorem. For the mean value theorem, we still need to plug in our values, but this time we're not trying to make sure they're equal. They don't have to be equal. This time we need them so that we can take the ordered pair, which here we have 1, 1, and here we have 4, 4, and use them to do the slope formula, because that's what this part of the equation is. 4 minus 1 over 4 minus 1 gives you 3 over 3, which is 1. Now we need to take the derivative and set it equal to 1. Well, 5 minus 4x to the negative 1 is equivalent. The derivative of that would be positive 4x to the negative 2. So we get 4 over x squared, or 4 equals x squared. I just multiplied x squared by both sides. Then you take the square root of both sides and you get plus or minus 2. However, we can't use both of those. The reason for that is because of our interval. Our interval is only from 1 to 4, so we can only use positive 2. Make sure with these that you're checking your interval and making sure your answer falls within it. Okay, number 5, find all the intervals for which this is increasing or decreasing and find any relative max or mins. So I take the first derivative because that's where I find out about increasing, decreasing, maximums, and minimums. Okay, now we need to see what all the pieces have in common so we can find the critical numbers by factoring. 4x appears to be in common, so we'll pull that out, leaving us with x squared plus 5x minus 14. So that'll factor to be 4x, x squared, x plus 7, x minus 2, and we get three critical numbers, 0, negative 7, and 2. Now we need to use these critical numbers to create our chart. So we do negative infinity to negative 7, negative 7 to 0, 0 to 2, and 2 to infinity. And we need to take a test point from each one of those and plug it back in the derivative. Now I'm going to do this rather quickly, but you can go back and check any time. You can plug your test points into any one of these three equations. They're all the derivative, they're just different forms of it. I'm going to use that very last one, the bottom one, because I find that easier to do in my head. So if I plug in negative 8, that gives me a negative, and a negative. So 3 negatives makes a negative. If I plug in a negative 5, I get a negative, positive, negative, making a positive. If I plug in 1, I get positive, positive, negative. If I plug in 3, I get positives everywhere. Now the negative in the derivative implies the original is decreasing. A positive in the derivative implies the original is increasing. And we just follow that pattern all the way through. So now we clearly have where the function is increasing and decreasing and on what intervals. Now we can use this same information to draw a quick sketch, decreasing, increasing, decreasing, increasing, and see that we have minimums at negative 7 and positive 2. Make sure you put x equals for those. And we have a maximum at 0. For number 6, find the intervals on which the graph of the function is concave up or down and finding points of inflection. We follow the same pattern and process we did in number 5, but with the second derivative. Concavity and points of inflection are going to come from the second derivative. So the second derivative here will be 12x squared minus 24x. I set it equal to 0, factor out a 12x, and I get 0 and 2 as potential points of inflection. So I'll do negative infinity to 0, 0 to 2, 2 to infinity. And here we're plugging test points in the second derivative. So again, you can plug it in here or here. I'll use the second one. If I plug in a negative 1, I get negative times negative, which is positive. If I plug in positive 1, I get positive times negative. Plug in 3, I get positive, positive. That would tell us that f is, if the second derivative is positive, f is concave up. If it's negative, f is concave down. If the second derivative is positive, f, the original, is concave up. So there, clearly, you have the intervals where you're concave up and down. And since the concavity does change at both 0 and 2, both of them are points of inflection. Please remember they are points of inflection, not points of interest. I know what your GPS tells you for POI, but this is calculus, so POI is points of inflection. 7. Find the intervals on which f is increasing or decreasing. Okay, nothing tricky here. We're increasing there and there, which would be from negative infinity to negative 2. Always focus on the x values. And also from 0 to 2. So that's where we're increasing. And then decreasing would be from negative 2 to 0. And also from 2 to infinity. Make sure you're focusing on x values there. I know this is going down, but it's also going right, which is what we're focused on, the x values, so positive infinity. 8. State the intervals in which f is concave up or down. Well, best I can tell, it's concave up from negative 1 to 0, and then again from 1 to infinity. That's where it's shaped more like a U. Now here, we're shaped more like an N, or lowercase n anyway, so we're concave down from negative infinity to negative 1, and from 0 to 1. Make sure you can recognize concave up and concave down. Finally, at the given point, would the first derivative be positive, negative, or 0? Okay, let's talk first about the first derivative. The first derivative tells you about increasing and decreasing. It tells you about maximums and minimums. But ultimately what it comes down to is slope. The first derivative is about slope. So what is the slope right here at this point? Well, hopefully that's clear to you now. It is 0. Just to give you a little bit extra practice here, if the point was here, our slope is negative because we're going downhill, so then we'd have a negative first derivative. If it was here, we're going uphill, so we'd have a positive first derivative. But at the point that was marked, the first derivative would be 0 because the slope there would be 0. The second derivative ultimately tells you about concavity. So you need to look at the concavity at that point. Well, here we look more like an N, so we are concave down, which means the second derivative would be negative. And that completes your review sheet. Don't forget to look over the AP questions we did in class as well. And between the review sheet and those, you should be well prepared for the test.